For our videos on quantum computing, it gives me great pleasure to welcome Professor Bindu Bambah, Professor of Physics at the University of Hyderabad and Joint Professor at the Center for Women's Studies. Professor Bambah did her BSc Honours and MSc Honours from Punjab University, Chandigarh, with distinction in all subjects and winning the first-class gold medals. She then got her PhD from the Enrico Fermi Institute of the University of Chicago in 1983 under the supervision of Nobel laureate Professor Yoichiro Nambu. She has served as a visiting scientist in the International Center for Theoretical Physics at Trieste in Italy, as a scientific associate at CERN in Geneva, and as a UGC scientist at the University of Madras, Punjab University Chandigarh, and University of Hyderabad, and then as reader at the University of Hyderabad and professor of applied mathematics at Punjab University Chandigarh. Dr. Bambah was awarded the UNESCO ROSTCA Young Scientist Award for South Asia in 1991. She has authored 132 research papers, garnering over 7,600 citations. She has worked on the nature of the quantum chromodynamic vacuum and the physics of strongly interacting systems, on new coherent states in quantum optics, isospin squeezed states, and on the interrelations between particle physics, plasma physics, fluid dynamics, quantum optics, and cosmology. Her theoretical studies on the quark gluon plasma address the problem of thermalization and stability of this plasma. Her recent research interests are in neutrino oscillations and quantum computing.
Let me start off by asking you to tell us a little bit about the history of quantum computing. I mean, in what way is it different from classical computing, and also personally, how did you get into the field?
Okay, so that's a very interesting question of how did I get into the field? So, I am now nearly 70 years old, and I have seen computing from the day the first computer, I think, came into India. And I didn't use it, I was too young then, but the first computer that I did see was an IBM 1620, which I saw in 1974. So it's been 51 years since I've been seeing the computer, and I thought it would be interesting to tell you about this journey from this IBM 1620 to the quantum computer that we're talking about. So in my mind, there is this echo of this full journey that I have been through live, seeing computers like this, and like I can see this. Yeah, so this is actually the computer that I used, and it's in a huge room with data tapes, and there's a phone, not a cell phone, and there's a dot matrix printer, and we had to wait days and days to get the result. And this is a quantum computer, and this is the journey
I started my first computing around the same time. I was in IIT Kanpur, 77.
Yeah, the previous one. This is a computer in IIT Kanpur, because we didn't have it in Chandigarh where I was studying. So we had to be shipped off to IIT Kanpur to carry out our work. And that I showed you, that is in IIT Kanpur. And we had to go there and and stay there in the hostel and wait for days for our result to come out and then take it back to Chandigarh. So it was this is the way we operated. Now you're here, you have this fancy IBM computer, which basically, and this is the Microsoft chip, which is on a which is on a little chip, and it is much more powerful, and it does work in a few seconds. So this journey has been sort of a miraculous journey for me. And I got, for the journey from the IBM 360 down to the IBM quantum computer has been, has had a lot of milestones on the way. But the way life has changed, and the thing is that, and one has to adapt to life. And I thought that it would be interesting to, for me, with this sort of experience, to convey the joy that I get from the advances in computing, and the joy I get from the fact that we've gone from classical to quantum computing. And the question as to why did I get into quantum computing is because my problems refused to stay classical. So I had to evolve with just like, a system, quantum mechanical system evolves in time according to Schrödinger wave equation, or I had to also evolve in time, and I had to get into quantum computing.
So
And
when was that? When did you start getting into quantum
so
computing?
I got into quantum computing through my work in neutrino oscillations. And also through my interest in analyzing data from particle physics experiments. They are so one had to learn machine learning in order to get into analyzing large amounts of data that came out in particle physics experiments. Then one got into when one went to Fermilab to do this, and Fermilab is where the quantum computing center is being developed. And so, my students had to start using some of the machine learning techniques, and then they thought, well, it's more efficient to use a quantum computer. So at the moment, of course, we were just doing standard problems that we had already done on a classical computer and mimicking it on a quantum computer to see how much faster they are. We have not yet developed any actual algorithms for the quantum computer, but that's what I hope my students are doing now, because I have sort of retired and I just overlook if they ask me any questions, but they are now, they have got their PhDs and they are looking into these on how to actually implement new algorithms on the quantum computer. What I was able to do was to take classical algorithms that were already developed and look at them on the quantum computer. And of course, the quantum computer has not evolved to the extent where it could handle the type of problems that we want to handle in particle physics. But hopefully we will get there. And I'm interested in the direction this takes. Whether we really will. I know machine learning is doing us a lot of good. Whether actual quantum computing will do us a lot of good, we still have to see. But it's a great adventure.
So why? But what is different about quantum computing, and how does it help? Why do we need to get into quantum computing?
Okay, so let me just. The one-word answer is efficiency, but let me just get into the nitty-gritty. Okay, for that, I have to first define a quantum computer. So a quantum computer is a machine that performs calculations based on the laws of quantum mechanics rather than on the laws of classical mechanics. And how is this different from normal computers? Well, first of all, this is part of a lecture series on quantum mechanics, I'm sure the people who have already listened to your lectures know what quantum mechanics is. And so what we are trying to do is leverage some of the quantum mechanical principles to form these quantum computations. And before I get into the history, let me just, so first let me get into the history of it, and then one will find out what the methods of leveraging are. So a brief history of quantum computing is as follows. In 1980, Benioff showed that a computer could operate under the laws of quantum mechanics. And what he showed is that something called a Turing machine, which is sort of a model of a computer, could be operated upon by the laws of quantum mechanics, as the evolving data could be described by a Schrödinger wave equation. Then Feynman introduced the idea that quantum computer could efficiently do problems which classical computers couldn't, and specifically physics problems. That wasn't taken it was taken seriously, but it was Feynman, so everybody thought the idea was very difficult until David Deutsch was the first person who showed that the computational power of quantum computers is much more than classical computers. And then a whole bunch of people, particularly Shor and Grover here, Love Kumar Grover and Peter Shor, they tackled a few problems which are very hard computationally, and they showed algorithms which speed them up a lot on a quantum computer. And then these were all simulators until, of course, actual quantum computers, they tried to build them. And that was because one learned how to handle quantum mechanical devices very efficiently, particularly following the work of quantum optics people. They were able to actually develop actual quantum computers in the lab, and then quantum gates and circuit models, etc., for quantum computers came up. So this is the brief history of quantum computers, and this is the first. So I still haven't answered your question, but it'll come as I go through the history.
Yeah, but you've introduced the term qubit. So can you define what
yes,
is
I will.
a qubit?
I will go through that. So okay, so let us say that this is the first paper on quantum computing, and I told you what Benioff's model showed us is that there is a evolution along a computational path which allows for a superposition of states. Now, let me just tell you what I mean by this. Okay, so for example, and what Benioff did is use the classical the analogy of a coin toss to distinguish what is a classical computer from that of a quantum computer. And this analogy comes up again and again in any description of a quantum computers. But Benioff was the first person to sort of use it. And he said that, in a classical coin, if you toss it randomly, there are two outcomes, heads or tails, right? And so that is all. I mean, you can always predict that a classical coin 50% of the time will be heads and 50% of the time will be tails. But now suppose you have a quantum coin. So what the quantum coin is that when you toss the coin and you spin it, now along the path of between the time when you toss the coin and when it lands, okay, you can have a number of states, an infinite number of states actually, because it's a spinning coin. At a given time, the coin is a superposition of heads and tails along. And there are infinitely many states along which it is a superposition of heads and tails until it lands. And then you have sort of what is called a wave function collapse. You have collapsed the coin into a state of heads or tails. But along the way, you have an infinite number of states in which the coin can be in. Whereas in the classical case, it can only be it can only be heads or tails. But along the spinning coin, along the way from it being tossed and land, can be in a set of head and tails.
Okay, so maybe I'll ask you an unfair question here. When before the coin lands, I really can't say whether it's heads or tails, because it's only when it lands, like equivalent to performing the measurement, that it's either heads or tails.
Exactly.
Until that, so why can't I say that the coin is in a superposition of heads and tails?
No, you just start flip and it flips. It's not, I'm talking about just taking a coin and tossing it. Okay, and you just flips and it lands, right? It can be heads or tails. Whereas in the action of spinning the coin, along the way, you have a collection at which any point on the way, it is a linear combination of both. So this is what the coin analogy basically, this is the difference between a quantum, a classical coin toss and a quantum coin toss. Let me just explain it a little more, because the coin, this is too much of an analogy. Let's do it.
Right. Yeah.
Let's do it more concretely. So what Feynman did in his paper was say that because of this property of there being all these different possible states that a coin can be in, that the complexity of the problem becomes more, and quantum systems then can solve problems faster, and I will explain that. So I will I will just go straight to the okay. So the coin. So a bit would be like up and down. Okay. So when you have a 0, it's say heads up, and if you have 1, it would say tails up. Okay, so a normal system, which is a bit, has either a 0 or a 1. A bit is in either a state 0 or a state 1. Whereas what a qubit is, it's a linear combination of the state 0 and the state 1 are states which are eigenstates of a quantum mechanical Hamiltonian, and a qubit at any point is follows so the evolution of the state follows Schrodinger wave equation, and in Schrodinger wave equation, when a state evolves in time, it evolves as a superposition of the possible eigenstates of the system. Okay, so and as they evolve, states can also undergo something called entanglement, and so they can be correlated over large distances. So this also enables quantum algorithms, and also the states can interfere. And so this can also these 3 properties of quantum mechanics, that is, states evolve as superpositions according to the Schrodinger wave equation, that they are able to be entangled or correlated over large distances, and that there is something called quantum interference in order to amplify correct solutions. These 3 properties of quantum mechanics are the characteristics of qubits as opposed to classical bits 0 and 1. Okay, a classical bit 0, until acted upon by some sort of a gate in an electronic circuit, will remain 0, and then it will switch to 1. But it will never be a linear combination of 0 and 1. Whereas a quantum bit or a qubit, it can be 0, it can be 1, but it can be infinite many linear combinations of 0 and 1 also. So that is the difference between the classical bit, which is just deterministically 0 and 1, and a qubit, which can be all possible combinations of 0 and 1. Okay, so that is the basic difference between a bit and a qubit. So as I said, that quantum states, they are solutions of the Schrodinger wave equation, and the way they evolve in time is by some unitary operator. And so when you measure a wave function, then you specify a specific location and a time, and then it's a probability that the wave function will be there, and the probability is psi squared. But between measurements, the quantum system can evolve as linear combinations of the system. Because if psi is a solution and phi is another solution of the Schrodinger wave equation, then a psi plus b phi is also a solution of the Schrodinger wave equation. So if we have a system evolving by the principles of quantum mechanics, then it can be in a superposition of this eigenstates of the system. So
the measurement
so
process,
for example,
I was asking the measurement process itself
yes.
is not followed. Is not following Schrodinger evolution. Is that right?
No, the measurement process is at that point when you measure, then you have collapsed the wave functions to one state. So when you measure, then you do not measure the superposition, but you measure the state that it falls into. So in that sense, the measurement kills the superposition. And so the way we represent it is if you have the 2 bit states as 0 and 1, then at any point, it can be either, or maybe, on and off, or spin up or spin down. These can have, 0 and 1 can have many different physical meanings. Usually we take them to mean spin. In quantum mechanics, usually these states are spin eigenstates, where this is the spin up eigenstate and this is the spin down eigenstate of an atom or an electron. Or it can be polarization states of two photons. So that is what the physical object of the bit would be. And the qubit would be a linear combination of the two. So what happens is, in classical computing, you would have only two states, the spin up state and the spin down state. That is the head states or the tail state, or on and off states. Those are all the information would be encoded in these two states. These two states would be called the basis states in quantum computing, upon the evolution of these states, they can be any linear combination of these two states. Okay, so not only do we have the classical states inbuilt into quantum computing, but we have all these extra states, which are the superposition state, which are there in quantum computing. So in that way, quantum computing, the principle of superposition in that way makes quantum computing have a lot more states in which you can encode information besides just the states 0 and 1. So that is the power of quantum computation, is that it gives you a whole bunch of more states in which you can encode the information. So usually a bit of data is represented by let's say a single atom. Okay, and so this would be the state 0, in which the electron is in the ground state. This would be, and the way you change a state quantum mechanically in a quantum computer, the way you would change a state would be that you would put a light pulse or a laser pulse or a microwave pulse onto the bit, and it would change into another state that may be an excited state, which would be the state 1. So it would be a 2-level system. And the way you would evolve it is by change one state to another is by means of a light pulse in an actual physical system. Okay. But on the way, if you have two states that are the basis states 0 and 1, then all possible states that the qubit can have can be encoded very nicely onto a representation of a qubit, which is called a block sphere. That is that you can go from the state of 0 to state 1 by performing rotations on this sphere. Okay, and this is called the block sphere. And in terms of the angles of the sphere, this is how you can represent the superposition of the two states. So this is a very convenient way to visualize the superposition of two states. That is, all the states on this sphere are the possible states that a qubit can be in upon evolution. So these are all the states that are available to you for encoding. Okay, and how does that? So that is the explaining what is the principle of superposition. Now let's go to the next.
The theta is representing your the amount of the amount of 0 versus the 1 state of the qubit.
Yeah.
What about the phi? Why do you need the phi?
The phi tells you the phase, because what happens is that when you measure something, so the phi tells you sort of the evolution. When you have the eigen state psi, it is a complex eigenstate, and it is the so this encodes the fact that you have a unitary evolution, which tells you how the phase of the wave function is changing.
Okay.
Okay, but it will not make any difference. It will not make any difference to the measurement of the state, because when you measure the state, you will take the expectation value. You will take psi squared, so this phase will.
Yeah. So the solution of the Schrodinger equation has that
demands
phase phase invariance, but then when you interfere or interact different particles, then the phase will come into
phase will come in. So when quantum interference has to come in, for example, then the phase is required.
So let's now go on
and we will show you that there are gates.
Entanglement.
Yeah. So, and also there are gates which implement the phase, and there are gates which implement the rotation also. So, so it's very useful. I mean, this is a mnemonic, but it's a useful mnemonic because you can have then gates which take you around this sphere, and these gates can be represented by matrices, and that is very convenient mnemonic to use when you are looking at superposition and creating more states. Okay? These will be useful. So we come to the next topic, which is important in encoding, and that is quantum entanglement. So the thing is that what quantum entanglement is to quantum computing is that it can allow quantum computers to perform multiple calculations in parallel. So that is it. So this property which quantum mechanics has and which states can have allows quantum computing to be more efficient. The whole our whole idea behind introducing the quantum computer is that you will make the quantum computer much more efficient using the laws of quantum mechanics rather than classical computers. So so all of this is the machinery that makes the quantum computer more efficient. So let us see how it works. So what it tells you is it allows particles to exist in multiple states simultaneously. That is, you can have a particle in different states, and there is a correlation between different states. So even when these particles are separated by large distances, they still remain connected. And so let us see, the only time when this connection stops is when you measure one of the states far away. And what it tells you everything about the other state with which it is entangled. So let us see what I mean by that. So how do you study? How do you know this entanglement? How do you study? Well, you take a system and you generate two particles from the system, and for example, you take a system. Let us take a nuclei which has spin 0, and it decays into two particles. One which has spin half, and one which has spin minus half. Okay. So at a given position, when this state decays, it initially was in a spin 0. So when it decays into two spin half particles, one will be spin half and the other will be spin minus half. Now these particles then travel far away from each other, but one doesn't know the spin of these particles until one measures one of these particles, and one finds out that the spin of this particle is minus half. Then automatically one knows that the spin of the other particle, that was its sister, is spin half, even though this particle has been measured thousands of kilometers away from its origin. So that is a result of superposition. And and what this phenomenon is called, in which one particle's knowledge, one particle is so enmeshed with the other particle that when you know the characteristics of one particle, you automatically know the characteristics of its partner. That phenomenon is called, quantum entanglement. And this is the phenomenon of quantum mechanics that really bothered Einstein a lot, because Einstein thought that this is sort of counterintuitive, because how can you know the characteristics of the particle, so many, so far away from the particle? That is, how can you know, I'm going to have an action at a distance? So this was contemplated by him with Podolsky and Rosen, and was called the EPR paradox. But in quantum computing, this particular paradox is leveraged into making a number of parallel measurements which are dependent on each other.
Yeah,
Okay,
so his prejudice was probably because of the fact that in relativity had essentially abolished the Newtonian conception of action at a distance, and here was action at a distance creeping back into physics, right? So
exactly.
it made him uncomfortable. Right?
It made him very uncomfortable.
Yeah. So you said that a measurement destroys the superposition, right?
Yes.
Would it also destroy the entanglement? Well, because it collapses the other particle, right, into the particle
so
that you're
once you have measured the particle, then you know what the properties of the entangled particle, initial entangled particle, was. So once you measured the particle, then it is no longer entangled with the other particle, but it is entangled in the sense that you know what the other, in your mind, they are entangled.
The results, reality, the result is it.
Okay. You see what I mean? I mean, entangled in the information that your mind deciphers from it, or the instrument deciphers from it. But then the particle, when you measure it, ceases to be entangled, because the superposition, as I told you, stops there, right? Because you already collapse the wave function. So for example, how do we create entangled qubits? Well, we have to take 2 electrons or 2 photons. And if they so their joint state cannot be written as a product of individual states. So the quantum state is that a particle can be either, the A particle can be in up position and B particle can be in down position, or A particle can be up position and B particle can be in down position. I'm talking about the example of the 2 electrons going away from each other. We don't know which one is up and which one is down, right? Until we measure. So at a given point, its wave function is such that either one can be up or down. So it cannot be written as a product of this is up and this is down, but it has to be all linear combinations of this up, this down, and this down, this up, right? I hope that can be seen. Yeah. So we now separate these particles, sending one to Alice and B to Bob. I don't know, Alice and Bob are very occur in all sorts of computer scientific work.
Yeah, A and B basically.
A and B. Yes. So once Alice measures her qubit and finds it to be 0, then Bob's qubit must be 1. And if Alice finds 1, then Bob's qubit must be 0. So in that sense, once the wave function collapses, it ceases to be in a superposition or state, and it becomes one of the other states. Okay, so then it is a product state, Alice being in 0 and Bob being in 1. So so the entangled state cannot be written as product of the individual states, but once they collapse, then the quantum states collapses to a product state. Okay,
and the collapsed state is like a classical product.
It's like classical state, yes. And the interesting thing, and the one that really made Einstein uncomfortable, was this perfect correlation holds even if the qubits are physically far apart. So basically, entanglement is a non-local property of quantum mechanics, and this is what irritated Einstein a lot. So basically, the way it is often explained is that if you have, a ball which is yellow at one side and red at the other, and it's spinning, you say that it is a superposition of both yellow and red. But when you when it is when some the first one is yellow, the other one will also be yellow. When the first one is red, the other one will also be red. So until you observe the balls, you don't know whether the ball is red or yellow. It is a superposition of both red and yellow. So this is many ways of
So
saying
yeah,
the same thing.
until you measure it, or until your partner measures it,
Or
measures the
until
other
your
one.
partner measures. When your
Measures
partner measures it also,
the other one, yeah, the
you are determined. So yeah, so it is so measurement produces a classical outcome, as we were talking. Okay, and it is irreversible, probabilistic, and non-unitary, because one can't go back now. Okay, and so evolution are so before measurement, everything is unitary, reversible, and deterministic. So does measurement destroy a superposition? Yes, with respect to the measurement basis. So it's measurement. So superposition itself is not fragile. Whereas the measurement process ends the whole party of superposition. Okay. So what entanglement tells you is that quantum bits the fates of quantum bits are interlinked. So creating a single system where measuring one instantly affects the other, no matter the distance, allows quantum computers to process vast possibilities simultaneously for complex problems. And so it's like having linked coins. If you flip them and one lands on heads, you instantly know the other state. But unlike classical coins, entangled qubits exhibit superposition until measured. So so you can carry out parallel computation among all the different superposition states in the system. So let us just, this is what is quantum parallelism. And what it does is that it gives you exponential powers of the system. Okay, with 300 qubits, as opposed to 300 bits, which would only be 2 to the which would only 300 times 2 your system would become. With 300 qubits, you have more processing power than the particles in the observable universe. About the power of superposition is that, how, for example, value stored in a classical register, and that the corresponding would be stored in the basis states of the quantum register, but you can have all these states also besides these states. So which is the power of superposition. For example, for 300 electrons, you can have 2 to the power 300 or 10 to the power 90 complex coefficients. So that is, the number of qubits is more than the number of atoms in the universe that you can have storage in quantum computer, technically. So this is the summary. Classical computers use bits, 0 and 1. Quantum computers use classical computation explores possibility one after another, whereas quantum computation has something called quantum parallelism, which have all these entangled states, and you can explore possibilities in parallel, but extracts uniform information in a very constrained way. So you can think of classical computing as bookkeeping and quantum computing as doing accounting while humming. That's what a good.
We will stop here for today, and after a brief historical diversion, we will continue with our discussion of quantum gates, quantum computers, and emulators with Professor Bindu Bambah.